Ladies and gentlemen, welcome. So, in our last time in the last episode, we set up some station circuitry, some Trainyard station circuitry, and now we need to basically set up more circuitry to actually dispatch the train, to evaluate when a train should be dispatched. And then, aside from that, we are also going to need some circuitry to turn these stations on and off. I think I'm not entirely sure if that's actually necessary, but we'll see. Let's dispatch trains first. Okay, so under what circumstances does a station dispatch its train? So first of all, when the type of it, the type of the train is actually the correct one, which means the L or U, so type of train is in demand. Right? And further, because we also need to be able to tell how many trains we need, for that we have the counter system, right? So we're also going to release the train if its count, if I mouse over here, we can see U2 L7. L7, why L7? What made that happen? Gotta find out where the yeah, of course. This you're going to feed onto the red wire here. No, we're actually not. It's going to go up north. So the problem here is if I feed it onto the red wire, watch what happens. Watch the red numbers. Do you see that? We can't do that. So we can't feed it onto the... if you wanted to feed onto the green wire, we would have to do it up here. The problem with that is if somebody copies the setup to more stations, to get more stations, it would end up in a situation where the wire that goes from here, to this power pole just gets copied into each single instance, and as you just saw, we can't have that because that'll just get us a loop. So first of all, we need to figure out whether or not the train in the station is of the right type, and then we need to see whether or not the number of demand here, L7, right? If the station is smaller or equal to that demand. So if I look over here, this should be L2, and then over here on the next one, this should be L1. And we're basically going to say, in this case, for example, if we want to dispatch loading trains, we're going to have a check in here that says, is the L on this as big as the L on this? Or is it as big or bigger? Or as long as basically the recognition here that I'm actually going to have to change the numbers on the station here, L and U, because we can't easily compare otherwise. Well, we'll get to that. We're basically going to see if the local L or U is equal or smaller than global LU. So we're going to compare the local counter with the number on the global network, and if it's the same, so 7 or if it's smaller, so anything from 7 and down, then the station will send its train. And the reason we're doing it that way is because if we have, let's say we only want to dispatch 14 trains to be unloaded, but as you can see here, we have 20 trains that could be sent, right? And we don't want to send 20 trains if you only need 14. And that's why if we say, okay, each station checks whether or not its counter number over here, the one that's, as you can see, if I go down, it gets smaller and smaller, right? 18, 17, and so on. And as long as the number is equal or smaller than the global number, the station will release. So we automatically stop at 14. Right, as you can see, 14 and 14 over here as well. This will still send the train, but up here, we're already at 15. This will no longer send the train. That's how we're going to figure out whether or not we want to release the train. So I need a circuitry that checks whether or not the current train in that station is in demand, so that we can decide what we check on. And we're going to give trains that need to be unloaded a one that tells us that there is stuff inside, and trains that need to be unloaded a 0 that tells us there's nothing inside. That's basically what I'm going to use here for the okay. This is the one. E one. And the load equals 0. There's nothing inside. Okay. Or should I use, I could use F, and it probably makes more sense if I use E and F instead. Or supposed to say 0. Is F for full. full cargo. Empty cargo. Yeah, this makes more sense. So it's a lot of repeating the same thing over and over, same actions here, but hey, things take a little bit of time to set up properly. Okay, so you have here the information of what kind of train it is. And now I need to use that to inform the next circuit. I can do that by going negative. So here, yeah, times -1, times -1. We have now inverted the one we are using. I'm gonna drive you out of the way for a second here. So here's the following problem. Of course, this combinator, the counter, I could probably actually do it. No, it still end up with the same problem. The problem I'm running into is that I don't really have a very easy way of splitting, of just negating one or the other based on what this tells me, right? Because they're the same signals. Here I say if I have an F, so the train is full or has items in it. Doesn't actually have to be full, just has to have items in it. Then I want to only see the F, I want to ignore the E. The problem is, how do I filter out the E while also then still having the E when another train is in here, when an empty train is, right? So this needs to be a setup that fluidly switches back and forth between the two and always filters out the one that I'm not currently in. So I can't do anything manual. It has to be something that happens automatically. And I can't just use maths very easily because they're the same signal. So if I say, okay, if F is bigger than 0, I basically contaminate the F over here, the F20 here. I turn that into F21, for example, so I can't just use easy math. It's a bit complicated. This is not gonna work, I don't think. I need a whitelist filter. I already have a bunch of those. Where's my stuff? Okay, let's see these. Where are you? Here. Hey, sorry about that. So what's the difference between these? It's 4 and 4. Okay. Let's move this forward a little. So this automatically excludes everything that is negative. and this chooses only positive things. What's happening here? So the green wire has information from this combinator, and this combinator. Info comes in, gets filtered for positive stuff only. This one essentially only takes info from this box over here. Okay. Oh, this is an addition, yeah. Greater equals 0. If we stop time for a second and disable these, let them run the course, stop time, advance a couple ticks, turn this on, turn this on. This circuit is a tick faster. Okay, test 1 complete. And let's stop typing in. Advance a few ticks, turn them on, 1 and 2. I did not like that. Let's change what we have here and let's turn that into E14 F10. And we want status information. Bounce a few ticks and then turn these on. Okay, so this one has a cleaner signal when the filter is changed, and this one has a cleaner signal when the main is changed over here. Oops. Wait, I needed to... Dang it. Let's see that one more time. No, this is... Wait, what? It's the wrong way around, actually. Right. Yep. Yeah, okay, now I gotta test that again. Turn on, turn on. What happens here? I mean, the signal is dirty, right? That should not be showing for my purposes. Now it's correct. And this is a tick late, but it's clean. The first signal I get is clean. Okay. And turn it back on. So this one, I need to see that again. I need to remember that I did it correctly. E14, F10. But this one gives me a signal I don't want. This gives me the E before. Dang it. What happens if I change this, let's say 27. Okay, there's no contamination in any way, but 0, 1. It simply switches over. There's no signal contamination for switching over on the okay. Okay. If they change in the same tick, everything is fine. I think I'm going with this. Seems like this whitelist filter has a cleaner signal on the out. Alright, how do I work that now? Do I actually switch it back so I can use it as a... Looks like it. A lot of repeating the same actions over and over, huh? If it's a U, and that's L. I'll leave that for now here, but I predict that I'll probably place this combinator in here, this way, and this combinator in here. That's probably what's going to happen at the end, but let's see how does this. So the filter goes in there. And the line in. Goes in here. And that's the out. Yep. U14. I thought it was 20, but it's actually only 14. Okay. That's the 20. There we go. Okay. No, wait, wrong wires. Okay, wait. That was actually. That's how it should be. Yep. There you go. And yeah. So we have now filtered the information from here, or used the information from here as a filter to pick either a U or L from out here, right? And now we can say if this U is greater or equal than the, and we're going back to, dang it, all right. This needs to go to load, so it's empty. Lots of brain farts today. This needs to go to unload, so it's full. And we'll just copy this all the way down here. So if what's coming out of here is yeah. If what's coming out of here is, dang it. I need to, don't I? Let me think about this. Basically, the idea is if the filtered signal over here is the same or smaller than what happens if then D and empty equal load. So we have a problem here. Need yet another set here to determine if f, wait, which one is it? If f bigger than 0, u. Okay, this should now work for our purposes. And we're leading these back. That's a bit of a stretch here. Okay. So if everything went correctly, why is this one outputting a D? U and L, yeah. F, F. So every empty train should be wanting to leave. E is smaller or equal to D. That's correct. F is also correct. Oh, so full empty. There was an error. I'd forgotten to adjust one of the combinators back to the new signals over here. So this is an empty train. This train should be wanting to leave, and it does. The same with this train, and it does. And then we have to find 15. This one should not. Wait, this belongs to this one. This should not be wanting to leave. And F, this one should be wanting. Yay, it's working. So in this case, load until cargo is full, unload until cargo is empty, and another train yard in between. Circuit condition, dispatch is 1. Wait, come back. Dang it. Yeah. Let's see if this is all working as I imagine it should. let's just leave this a little bit, run a little bit. Time to fix this stuff, these blueprints. Okay. So these trains should simply be stuck here, waiting until they're probably eventually needed. $14, $5. Trains that are done here do actually get to leave. And you up here. Get to leave once you actually have a reason to. Okay. So what happened here is that this simply went down further and further until it had no more items in the bank. If we let this run normally again. We should be getting trains to leave again. And ideally, we would slowly see trains actually stacking up here with loads, loader trains, except of course that we have exactly equal supply and demand. So the only way that would happen is if our demand slows down. So going to add we can only let these guys actually register the cargo. Because right now this tells me that there's no train here, right? That there's an empty train here, whereas there's actually no train, which is of course an issue. Because essentially what's happening is that the circuit over here takes longer to reevaluate whether or not the train should be dispatched than the train takes to get sent the dispatch signal. So basically trains are being dispatched before they're even finished evaluating. So that's what I'm going to do the next time. I'm going to build in some more features that take care of basically slowing down or delaying the circuit, the dispatch signal, until we actually know the correct measure here. Okay. Next time, save game. Thank you for watching.